Hi there. After kids seem to have some difficulty with the homework last night, I thought I'd put up a quick video on how to model multiplication. Multiplication basically starts with the algorithm, right? When we learned it, we started with the algorithm and we finished with the algorithm, and the algorithm was all we knew. And by algorithm, I just mean the procedure. If we had to do a multiplication problem, let's say we were doing 15 times 6, we would go ahead and do 6 times 5, 6 times 1, maybe do some regrouping or carrying if we had to, and then we had an answer, and that was that. The way it works is 6 times 5 is 30. We'd write down the 0. The 30 we wouldn't want in the way, so we'd put it up here. Some people would call it carrying, some people would call it regrouping. Then we'd do 6 times 1, make that a 6, add the 3 on, get a 9. Our answer is 90. Magically, we're on our way. Now, that is our end goal. We want kids to be able to get right through the algorithm, but we also want them to understand what it means, especially right now as they're first learning what multiplication is. And so this sort of goes back to when we were in, second grade, maybe being introduced to multiplication math facts, or third grade when we were sort of exploring them, trying to learn them, get them into our heads. If we had a math problem like, let's say, 3 times 5, the 3 means how many groups we have. The 5 means what size the groups are. And this is actually officially correct because the times sign that we use, it stands for the words groups of. So the front factor is always the number of groups. The back factor is always the size of the groups. We kind of interchange them just because the end result, the answer, is the same. I try to tell the kids that actually that product is not the answer. The answer depends on what we're trying to find out. In any case, we would have maybe made something called an array. And an array looks something like this. We take our number of groups, say we have 3 groups, and it'll give us 3 rows. And then each of those rows, we'd say, I want them to be 5 circles large. 2, 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5. We know that 3 times 5 is 15, and now by looking at these circles, we can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have a 3 by 5, which gives us 15 circles. Now we understand and can visualize what 3 times 5 means. Now, coming back to being able to actually accomplish multiplication, sometimes we're doing something like this, and we don't want to bother writing it down, so we might do it mentally. And as an adult or a proficient mathematician, we might say, hey, I know it's 15 times 6. I'm going to split this up into 2 easy problems. I'm going to split it up into a 10 times 6, since that beginning of the 15 means a 10, and I'm going to split it up into a 5 times 6, since the back half of the 15 means a 5. I'm going to figure each of those out, and then I'll put them back together. So 10 times 6 is my 60, 5 times 6 is my 30. I put those together, and my answer is still 90. Get 90 either way, whether we do the algorithm or whether we do this mental math way of doing things. I'm writing down the mental math. Normally we wouldn't. We'd just be doing these steps in our head. The thing is, now that we're going to be introducing multiplication, we want to say, how does this process go with this process? Because I got a 60 here, and I did not get a 60 here. It's hidden. First of all, we did a 6 times a 1. Kids forget sometimes. This 1 is in the tens place, so when we do the 6 times the 1, that really means a 6 times 1, 10, and we get 60 because it's 6 tens. We don't see the 60 because before we write it down, we take these 3 tens that we regrouped, put them with the 6 tens we just got, write down 9 tens. But it's still there. It's just kind of hidden in the algorithm. What we want the kids to be able to do is, if they looked at a picture, we'd want them to understand that it's still there. So let's say we had something like this. We'd ask ourselves, well, what the heck multiplication problem is that? Maybe not even realize it's a multiplication problem to begin with. We look at how many groups we have. 1, 2, 3, 4, 5, 6. And we look at how many are in each group. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Hey, it's our old friend, 6 times 15. Now, we have all that mental math stuff that we did. How does that map with having a big pile of circles? Well, ultimately, we've got this in 2 sections. We've got the 6 times 10 section, and we've got the 6 times 5 section. All that the homework asked us to do is notice, hey, there's a section right here, which is 5. There's another section right here, which is 10. So, splitting this up, this group of circles goes with our 6 times 5. This group of circles goes with our 6 times 10. That's all it wanted us to understand. The array goes with this sort of mental math style of breaking the math problem apart. For our arrays, we can tip them this way if we want and say we've got 15 rows and we've got 5 in each row. Officially, that would mean we'd probably want to have 15 times 6, but ultimately it doesn't really matter. All we really need to understand is that the 6 times 10 goes with a chunk, the 6 times 5 goes with a chunk. We can even flip-flop these. I could have done a group of 6 by 10 over here, and I could have done my group of 6 by 5 over here. The homework gave us a picture where some of them were colored in. It's just because 10 of them were one color, 5 of them were another. It still goes with mapping on this 6 times 10, this 6 times 5. This will mean I've got 30 circles over here. This will mean I've got 60 circles here. And if I put both of those groups together, I'm going to have 90 circles altogether. Once we talked about it, kids seemed comfortable with that, but there was a third aspect to the homework, and that was doing something called an area model. And with our area models, things got a little bit more complicated. They would say, all right, we've got that 6 times 15 math problem. We can draw that using area, using boxes, something that has a length and a width. And when we do that, we'd pick one side to go with the 6 and another side to go with the 15. It seems a little bit intuitive to us if we understand what we're doing that the 6 is going to go with this side. First of all, 6 is smaller than 15. Second, there's only one section on the vertical side of this, and the 6 only has one digit. The horizontal side is longer to go with our bigger number. It has 2 sections, which kind of maps to the way that this has 2 digits. We could call this side from here to here 10, and this side from here to here 5, and all together that would be a 15. This side, since it's not broken into chunks, is just a 6. Because each section has a length and a width, we can make those math problems. 6 times 10 and 6 times 5 that we had with our mental math way of breaking up the 15 and doing 2 math problems. Ultimately, 6 times 10 is 60, 6 times 5 is 30. We put them together and we can get 90 that way. When we start from scratch and draw our own pictures and kind of use it at our own pace to explain our own math problems, it all seems pretty easy. However, the kids were faced with something like this, where you have a bunch of boxes with a bunch more boxes with a bunch of boxes in a math problem, and it suddenly starts seeming overwhelming. It suddenly starts seeming there's a certain way you have to do things. For instance, one of the kids asked me, why do I have to put the 10 up here? You don't. You could put the 10 at the bottom. But when you've got to fill in the blank like this, suddenly it seems like this is the side where a certain thing goes. There's also a few counterintuitive traps here which messed some kids up. So let's see how this would break apart when they're giving you what they think is helpful fill in the blanks, but it's actually getting in our way of understanding how this 49 times 3 works. Our math problem is 49 times 3. we've got a box with a side, and this time it's really long. They're pretty comparable in size. How do you know which one goes which? Now you're kind of relying on the idea 49 is a 2-digit number. I'm going to be breaking that up into 2 sections, a 40 and a 9. The 3 is a single digit, so I don't want to break it up. In my picture, which side is not broken into chunks? This horizontal side. Which side is broken into 2 sections? This vertical side. That means our horizontal side is going to get the 3, and I didn't make that big enough, so I'm just going to write the 3 next to it. Our vertical side is going to get the 49. But then kids say, well, wait, there's a section over here and there's boxes over here. What am I supposed to do with those? This goes the entire length of the side, so it means we want the entire number. Whereas this breaks it into 2 chunks, so I want to take the 2 chunks of my 49, the 40 from the front and the 9 from the back, and put them in the spots. Technically, it doesn't really matter where you go. This picture is out of scale, so you could argue, since it's out of scale, you could put the 40 here and the 9 here. Most kids, it still feels a little bit more comfortable to them to put the big part of the 49 here and the smaller part here. However, that brings up another conflict. They say, wait a second, Mr. Kodva, this section's really short, and this section's really long. How come the 3 would go here and the 9 would go there? Again, the drawing's just not to scale. They're trying to reinforce the concept that this is a single-digit number, and we're not going to break it into sections. This is a double-digit number, and we want to break it into sections. Our goal here is not necessarily to make 49 times 3 easier to do. Honestly, the easiest way to do it is probably some version of mental math where you say, wow, that's really close to 50. 50 times 3 is 150. I'm only 1 shy on each of those 50s, so let me take away 1 for each use, and I get down to 147. However, it's probably also just as easy to do 49 times 3. 3 times 9 is 27. Regroup. 3 times 4 is 12 plus 2 is 147, because that's a 14. These 2 things are the easiest things to do. Why are we doing this stuff? It's just to understand that the 49 is really made out of a 40 and a 9, and they can be broken into sections. It's also to understand that the 3 is a single section, and ultimately it's going to be used to bring us toward doing multi-digit times multi-digit so that we have separate sections. That's maybe the scope of a different video. Finally, the kids say, Mr. Cooper, we've labeled all this stuff, and we still have more boxes. What are these for? That's where we take those multiplication problems from using the length and width of the box. So in this case, I'm doing 3 times 9. Wow, that looks ugly from being so small. And then over here, this box is still 3 going across, but it's 40 going on the side. Some kids flip-flop them, and they'll put the 40 times 3 like that. It doesn't really matter. I personally would prefer to make these uniform. If the times 3 is on one side, I'd like the times 3 to stay on that side, but it doesn't make a difference. Now, the picture is labeled. We kind of get it, but then we've still got all this fill-in-the-blank nonsense. And here, they specifically try to trip us up. They say, all right, I kind of get that I labeled the sides, and now this box, I can find out its size by doing 3 times 9. And this box I can try figure out by doing 3 times 40. And if I really wanted to, I could even write down that 3 times 9 is 27, and 3 times 40 is 120, and then I could put them together and I could say 147. But what's all this stuff? And you say, oh, well, these are our multiplication problems, and kids will say, oh, that's times 3, so they'd take the first thing, 3 times 9. But then they'd say, wait a second, this is 3 times 9 and there's a 9 over here. I don't understand what I'm supposed to do. They're making them have to recognize times 9 is part of this particular problem, so I need to put the 3 from the 3 times 9 here, meaning that this math problem has to be the other section. Okay, it has to be the 40 times 3. And on top of that, they're trying to trick them by flip-flopping the order. They didn't do it every time, but definitely one of the math problems had that. Once they do that, a lot of kids said, wait a second, Mr. Codeva, 49 times 3, shouldn't I put 147 in this box? Kids are really used to that idea of I do a math problem, there's an equal sign, and I put an answer. A lot of the kids were tripped up because they didn't think of this entire side as being balanced with this side. So that's something that we had to show them. We're saying this entire math problem is the same as this entire broken up math problem. Now finally, these boxes down here are just the spots where we put what these little math problems equaled before putting them together. 40 times 3 is 120, 3 times 9 is 27, and finally we put those together and make 147. It seems like a lot of work when we can just do this. It's meant just to reinforce the concept of multiplication. It's meant just to say the 49 can be split up into a 40 and a 9. The 40 is getting multiplied by the 3, the 9 is getting multiplied by the 3. When we do that, we're going to label different sections of a picture, and these sections of the picture go with different section of our math problem. That's how it all works. It takes a little bit of practice because it's not necessarily intuitive when we're used to doing multiplication this way, but ultimately, when we've practiced this and we kind of know where things go, our goal is to have kids be able to do this without making mistakes and also be able to do much longer numbers, 3-digit, 4-digit numbers, and for in 4th grade, multiply them by a 2-digit number, and I introduce them to 3-digit numbers. Hopefully that helped with understanding what the different portions were of that homework from last night, the arrays and then the area models. If you ever have questions, obviously, contact me at school. Thank you.